Welcome back. So let's see how we can put together the components that we've talked about recently into a single, very effective training algorithm. And this algorithm is called the Adam Optimizer. So in particular, what Adam does is basically, again, combining these components into an effective method. So it uses momentum. It uses this debiasing idea we talked about, which basically you divide the momentum by a constant as you are updating your parameter. It leverages adaptive learning rates. Okay. It also leverages pair coordinate learning rates. Okay. So such that you are adaptive to both the variance as well as the curvature of the loss landscape. Optionally, you can also leverage weight decay. Okay, and if you recall, weight decay was a technique that is useful when you want to regularize deep brain models and hopefully improve their generalization performance. Okay, so let's see what the algorithm is. So first thing first, you basically generate a mini batch, and you're going to use that to calculate basically the stochastic gradient. Okay. So you calculate the stochastic gradient. Now, if you're using weight decay, there are two ways to do that, right? So one way is to basically add lambda plus WT to the stochastic gradient, okay? And there is another way that I've written here, but we're going to talk about it in a minute, okay? But that's not quite important. So the first step then is to calculate the mini batch. Secondly, calculate the stochastic gradient. And this is one way you can, this is one place you can leverage weight decay. Regardless, the next step is to calculate the momentum, okay? Now, we talk about basically the bias of the momentum and why we may want to debias it by dividing the momentum. So here's what you can do, okay? So you apply the debiasing technique we talked about, okay? Now, this is basically integrating the first, I would say, component as well as the debiasing technique. Okay. So now let's see how we can leverage the other component we talked about previously, and that was adaptivity. Okay. So adaptivity basically meant that the learning rate depends on the stochastic gradients we have observed. Okay. So if you recall, it was something like this. So I had 1 over the square root of the sum of, let's say, the norm of gradients square, okay? And if we were using the pair coordinate learning rate, which we are doing here, we basically calculate this sum over the individual gradient coordinates, okay? So these three steps are basically meant to apply this idea of adaptivity as well as pair coordinate learning rate. So as we talked about before, we're not going to use a simple sum here. We're going to use exponential moving average to put more emphasis on most recent gradients. Okay. So we use exponential moving average to calculate basically the sum that's going to show up in the denominator, but we'll do that over individual coordinates. We also do the debiasing here as well, given the similarity between momentum and the exponential moving average, right? So, it may not be a bad idea to also apply the debiasing here, because at the end of the day, this sum is basically meant to estimate the variance, right? So over time. So we may gain some bias by using the exponential moving average, which we can get rid of, hopefully, by the debiasing technique. Okay, and then finally, we basically calculate our pair coordinate learning rate. Okay, and again, we have this kappa here to ensure we are not dividing by 0. Okay, and then finally, we update our parameter. Okay, so we go from current solution to the next one by basically moving along the momentum direction multiplied by a learning rate. Okay, so a couple of last remarks. First of all, as I mentioned, there are two ways to apply weight decay. One place you can add lambda times W here. Another place is to basically apply the weight decay here when right before updating the parameter. And this method is called the ADAM-W algorithm. Okay, so that's first remark. The second remark is that when you are calculating this pair coordinate learning rate, so there is another constant here, eta tilde. So this can be a constant, for instance, 0.001, okay? Or it can be something that you are tuning using one of the approaches we talked about before. For instance, you can tune this using exponential decay, and that's something that is quite, I would say, popular when you are training residual networks. Or you can use cosine annealing or other cyclic learning rate methodologies. Okay. And finally, one last remark in terms of the typical values of beta 1 and beta 2. So beta 1 is basically the momentum parameter. Beta 2 is basically the constant you use in the exponential moving average to estimate the variance. Okay. So if I'm not mistaken, beta 1 is roughly, again, these are big numbers as we have talked about before. So they are very close to 1. I think beta 1 is 0.9 and beta 2 I think is 0.99 or 0.999, something like that. But the idea is that both have to be very close to 1, okay? And this is actually something that we're going to try to demystify. Why I want the momentum parameter to be close to 1. We gained some intuition in our previous lecture, and we saw that when beta is close to 1, we are enjoying implicit mini-batching. But we're gonna nonetheless perform a more formal study of the role of momentum in training algorithms. I'll see you next time.